Hi friends, let us continue with capacitors, losses of energy on sharing charges. So you can imagine the condition that when you are sharing the charges between two conductors, what are the losses? So this you can share with the condition that suppose imagine you have two bottles, share different shape, different size, and then you are connecting them with some pipe. So obviously water will flow from one bottle to the other. The bottle which has higher water level, from there the water will flow to the bottle which has lower water level. The same way, you imagine two capacitors having different capacities C1 and C2, and when they are connected, then the charges will flow from one capacitor to the other, and this will flow till both acquire the same potential. See, water will flow till both have the same level. Remember, I gave you the comparison. The level of water is potential or voltage. The charges is water. So remember one thing, in doing so, in transferring water from one bottle to other through a pipe, the water is going to remain the same. Means here charges are going to remain the same before and after, before connection and after connection. So here what we are going to do is, we are going to take two conductors charged to a different potential, means two bottles having different water level. When they are brought in contact with each other, as I told, charge will flow from a conductor which is at a higher potential to the conductor which has the lower potential, and this process will continue till both have the same potential. In doing so, there will be some losses in the energy, and that is what we are going to find. What are the losses in the energy? But remember one thing, that charges are going to remain conserved before and after. So let's consider C1 and C2 capacitance of two capacitors. V1 and V2 are the potential, and the charges, say QF and QI. So law of conservation of charge, that total charge final is equal to the total charge initially. Means this is after connection, this is before connection. So as I told you, you can see here C1V plus C2V. Why I have written V? Because V is the final common potential after connection. V1, V2 were the potential before connection of two capacitors, and V is the final potential. So C1V plus C2V is equal to C1V1 plus C2V2, because we know it Q is equal to CV as per the definition of capacitance, and final charge is equal to the initial charge. Again I repeat, law of conservation of charge. Q final, finally the potential will be same. The process of transferring the charge will be till both have the same potential. So C1V plus C2V is equal to C1V1 plus C2V2. If you make V as the subject, it will be C1V1 plus C2V2 upon C1 plus C2. So now we know it. Yesterday's video we have learned that the energy stored in a capacitor is half CV square. So for conductor 1, before contact the potential energy is half C1 V1 square, and same way for conductor B, half C2 V2 square. So the total energy before contact is half C1 V1 square plus half C2 V2 square. Now after contact, See here, after contact, the potential energy of conductor A is half C1 V square. V square, both will be V square because after contact they have achieved the same potential, and that's final potential is V. So half C1 V square, half C2 V square. Again I repeat, because the energy stored in capacitor we have learned it's half CV square. So what will be the total final energy? This was the initial energy, initial before the contact. Now after contact, the final potential energy will be half C1 V square plus half C2 V square. I am taking V square common and I am substituting the value of V that already we had derived, value of V as C1 V1 plus C2 V2 upon C1 C2 in this formula. So I have substituted the value of V as C1 V1 plus C2 V2 whole square upon C1 plus C2 whole square, because it is V square. Then we are cancelling this 1 C1 plus C2. So this is the formula which we are having it, that is for final potential energy. We are going to find the loss in energy, that is initial potential energy minus final potential energy. Initial potential energy was half C1 V1 square plus C2 V2 square, minus we are going to subtract this as the final potential energy, that is C1 V1 plus C2 V2 whole square upon 2 C1 C2. When you simplify them just by taking the LCM, this 2 C1 C2 will be multiplied with this, and you are opening the bracket, so 2 and half, this 2 and this half will get cancelled, and this C1 will be multiplied here, so C1 square V1 square. Then this C2 will be multiplied here, so C1 C2 V1 square. Again this C1 will be multiplied, C1 C2 V square. Again this C2 will be multiplied, C2 square V2 square, minus open this bracket, A plus B whole square, A square plus B square plus 2AB. There is a minus sign before that, so all these three terms are minus. When you cancel the things which are getting cancelled, C2 V2 square, C2 V2 square, C1 V1 square, C1 V1 square. The things which are left is C1 C2 V1 square plus C1 C2 V2 square plus minus 2 C1 C2 V1 V2. So you can see from all these three terms you can take C1 C2 as common. So V1 square plus V2 square minus 2 V1 V2 upon 2 C1 plus C2, and this is nothing but A minus B whole square, so V1 minus V2 whole square. So the final formula is, this is very important formula. The derivation is not given in the textbook, but many a times the numericals come based on this. So this is the energy loss when two conductors which are at different potential are joined. After joining, as I told, the potential will remain same, and all these concepts are that the charges will be conserved before and after. So using that concept, we derive this relation that U1 minus U2 is equal to C1 C2 into V1 minus V2 whole square upon 2 C1 plus C2. So you can see this, that the V1 minus V2 whole square, it is a square. It means the U1 minus U2 term has to be positive. It has to be greater than 0. It means you can prove that U1 is greater than U2. So the energy after contact has to be less than the energy before the contact. And where this energy goes? So this energy goes or loses in terms of heat. Sometimes if initially V1 is equal to V2, it means, if you can see here, if V1 is equal to V2, U1 minus U2 is equal to 0, means there will be no energy loss if two conductors are already at the same potential. And many a times in numericals it will be given that one conductor or one capacitor is charged and other is uncharged. If another is uncharged, then initially you will be taking that the potential V2 is 0. If one capacitor is uncharged initially, it is like one bottle is filled with water and one bottle is empty. It can be like that also. One bottle has more water, one bottle has less water. So you, depending on conditions, but if one capacitor is neutral, then initially this V2 will become 0. I hope you have understood this energy losses on sharing the charges. So now let us go for the next topic. Next topic we have learned this, that when dielectric is introduced between this parallel plate capacitor, it induces the electric field which is opposite to the external electric field. This is the uniform electric field in parallel plate capacitor when air is there or no insulator or no dielectric is there in between. That is, there you have some external electric field, that is E naught. Now if you include the dielectric or you introduce the dielectric between this parallel plate capacitor, this dielectric get polarized. As a result, it will produce the electric field. You can see here, that is E induced, that is in the direction opposite to that of electric field. This we had learnt it, that what is the effect of dielectric. It reduces the external electric field, but it does not cancel it out. So let us study that first, why and how it is reducing the electric field when we are introducing a dielectric. You can see in this diagram that now the dielectric is introduced between the plates. So this is one plate, this is the another plate, this is a parallel plate capacitor, and dielectric is introduced in this. So as we have learnt it, that this because of polarization. So what is this polarization? So this non-polar molecules, they get stretched and the negative and positive charge gets separated. Then you can see here, this is the electric field. Electric field is from positive to negative. So this side there will be a negative charge and opposite there will be a positive charge. Say this is the atomic dipole. Now the next molecule will arrange in such a way that its negative charge will be closer to the positive of the first one, same and so on. So you can see this, that this plus charge will cancel this minus, this plus will cancel this minus, this plus will cancel this minus. But the charges here which are on the surface, that you can see this blue shaded, this minus charges on the left side and this plus charges on the right side. It means what is polarization? So when dielectric is kept, these charges will cancel each other, but there will be a charges induced on the surface. The net charges will be induced on the surface. Here it is minus sigma p because charges are on the surface. Minus sigma p, that is, it has induced the surface charge density, and minus sign because these are the negative charges. Same way here, this is plus sigma p because the positive charges are induced on the right plate. So basically, what is polarization? So polarization is nothing but, you can see here, polarization is nothing but, it is defined as dipole moment per unit volume is called polarization. Dipole moment per unit volume. So polarization is nothing but dipole moment per unit volume. Dipole moment, already we know, it is Q into 2A, charge into separation. Volume is cross sectional area into separation. This 2A will get cancelled. It is Q by A, and Q by A is nothing but sigma P. That is, the charges are induced on the surface when the dielectric is introduced between the plates of a capacitor, and when they are kept in this electric field, it tend to reduce this electric field. So I hope you have understood that polarization P is nothing but sigma P, that is the induction of these charges on the surface. These charges are induced on this surface, and this is known as polarization. So I hope polarization is clear. Polarization, again I repeat, it is electric dipole moment per unit volume. Dipole moment Q into 2A, volume A into 2A, 2A got cancelled, polarization Q by A. Q by A is surface charge density, the induction of charges on the surface. We understand one thing, this surface charge density plus and minus sigma P, it is induced. It was not before. This have induced when dielectric was kept in an electric field, and that is why it is known as polarization. Remember, we learnt these three methods of charging: by friction, by conduction, by induction. This is the fourth method. That time I told you that we will be learning polarization later on. So this is polarization. That polarization is nothing but dipole moment per unit volume, or you can write it is Q by A or sigma P, that is surface charge density which is induced. Also, polarization for linear isotropic dielectric, polarization is proportional to E electric field. So P is equal to, this is a new symbol, it is known as chi. It is known as the susceptibility. So P is equal to chi into E, and this is known as the chi E. It is the constant, and it is the characteristics of the dielectric. As I told, it is defined as susceptibility of dielectric medium. It is the susceptibility of dielectric medium, chi E. It is depends purely on the properties of the substance. So up to how much extent they get polarized, the value of chi depends on that. Some molecules may get polarized more, some molecules may get polarized less. So susceptibility of a given material depends on the medium. Say susceptibility of a vacuum is 0, because when there is a vacuum, no molecules whose charges can be displaced. So susceptibility of vacuum is 0, but different medium has different value, and greater the value of chi, that is susceptibility, greater the induced charge on it. It means it will get more polarized. Greater the value of chi, greater the polarization. So I hope it is clear that polarization is directly proportional to the electric field E, and that is chi into E, and chi is nothing but the susceptibility of the electric field. Same thing we are going to learn in magnetization. So that time we'll compare that susceptibility chi in electric field, susceptibility in magnetic field. So now we know that the effect of dielectric. We know that the resultant dielectric field inside the slab, when it is inserted, will reduce. E naught was the external electric field, Ei is the induced electric field, and both are in opposite direction. So E is equal to E naught minus Ei. Now we know it according to the Gaussian law. E induced, it is equal to sigma I by epsilon naught. E is equal to sigma by epsilon naught. So E induced is sigma I, या sigma p, whatever you say, sigma p or sigma I, which were induced charges, and sigma is only polarization p. So Ei is equal to p by epsilon naught, where p is the polarization, and polarization is nothing but epsilon naught chi E into E upon epsilon naught. So this epsilon naught will get cancelled. So E induced is chi into E. If I substitute these values, E induced value in this equation, I hope this is clear. See, basically E naught is epsilon naught, epsilon by sigma by epsilon naught, while E induced is sigma I by epsilon naught. This is the charges which we learned, which have induced on the surface, and this is only P. I told you sigma I, the induced charges are only the polarization. That process only is called polarization. If you substitute the value of E induced, this will be chi E. So E is equal to E naught minus chi into E. If you take E as on the other side, make E naught as the subject, E naught is equal to E into 1 plus chi. E naught by E is 1 plus chi, and E naught by E is nothing but you can write it this as even dielectric constant K or relative permittivity. So epsilon R is equal to 1 plus chi, and as I told you, the epsilon, the susceptibility is 0 for vacuum. So epsilon R, dielectric constant, is 1 for vacuum. So basically this already we have learned the definition of relative permittivity, epsilon by epsilon naught. So E naught by E is this. So you can see this relation is very important. It is not given in the textbook properly, but epsilon E naught by E is 1 plus chi. Chi is susceptibility. E naught is the electric field when no dielectric is there, and E is the electric field when there is a dielectric. I hope you have understood. E , E 0 is the electric field when there is a dielectric, and E is the electric field when there is a dielectric. I hope you have understood. E 0 is the electric field when there is a dielectric, and E is the electric field when there is a dielectric. I hope you have understood. E 0 is the electric field when there is a dielectric, and E is the electric field when there is a dielectric. I hope you have understood. without dielectric, and E is the resultant electric field when we have inserted the dielectric. Right? Hope guys you are clear with it. Now let us go next. Now these two things are again important. Capacitance of a parallel plate capacitor with a dielectric slab between its plate. Now first you understand this concept. Many times we have done it now, that let E naught be the electric field, E induced is the electric field which is because of dielectric kept, and E is the resultant electric field. Now we are making some twist in the story. You can see here D is the separation between two plates. Instead of introducing the dielectric throughout the space, means I am not introducing it throughout this gap, I am just introducing a dielectric of thickness T. So in this space and in this space there is air or vacuum, means there is no dielectric. The thickness of dielectric is T, while the gap or space between these two parallel plate capacitor is D. So we know that one thing is inside this electric field, means in this which is shaded region, their electric field is E naught minus EI, while in this unshaded region the electric field is E naught. I hope I am clear. And we have learnt that the dielectric constant K or epsilon R is equal to E naught by E. And this already we have learnt that when no dielectric is present, V naught is equal to E naught into D. Now when dielectric slab is present, this point is very important to understand. When no dielectric was there, nothing is there, then V naught is equal to E naught D, because E naught is the electric field when there is no dielectric and D is the spacing between them. So V naught is equal to E naught D. Now if we are introducing the dielectric whose thickness is T while the gap between them is D, so total V will be first potential due to this as well as the potential due to the unshaded region where there is no dielectric. In shaded region there is a dielectric, in unshaded region there is no dielectric. So we have to find out two potentials. First potential is due to this and second potential due to the shaded region. Now we know that potential V is equal to E into D. Here the electric field is, I have written it as E, while in this electric field is E and the thickness is T. So this potential is E into T, that is due to the dielectric. Now in the space without dielectric, the electric field is E naught and the gap between them is, you can see, is D minus T. This gap is D minus T. Here the electric field is E naught, the gap is D minus T, while here inside electric field is E and this spacing is T. So my potential will be V is equal to E naught into D minus T plus E into this thickness T. So what we are going to do is, we know it, C is equal to C by C naught is equal to V naught by V, because Q is same. So the ratio C by C naught is equal to V naught by V. What is the basic definition of capacitance? Capacitance C is equal to Q by V. Capacitance C is equal to Q by V. So C is equal to Q by V. C naught is equal to Q by V. So ratio C by C naught. Remember, what are C and what is C naught? C is the capacitance. C is the value of capacitance with dielectric, and C naught is the value of capacitance without dielectric. So remember, we have put a twist where the dielectric of full thickness is not there. So I am putting the value of V naught, that is E naught D, and I am putting the value of V here. I hope I am clear. V naught is equal to E naught D, and V is equal to E naught D minus T plus E into T. This is without dielectric. This is with dielectric, but only of thickness T. So V naught by V is equal to E naught D upon E naught D minus T plus ET. So I am dividing this equation by E naught. So E naught get cancelled. Here also E naught get cancelled. And here there will be E naught in denominator. But we know it, E by E naught is 1 by epsilon R, or 1 by K, that is dielectric constant. So C by C naught is equal to D upon D minus T plus T by K. And we are substituting the value of C naught, that is parallel plate capacitor, that already we know it. C naught is equal to epsilon naught A by D. So when you are substituting that value of C naught here, epsilon naught A by D, D minus T plus T by K, epsilon R. This dt will get cancelled, and ultimately what we are going to get, the formula is C is equal to C naught. C is equal to epsilon naught A upon D minus T plus T by K. Remember it, if only parallel plate capacitor is there, the C is equal to epsilon naught A by D. But this will be D minus T where there is no dielectric, and plus this additional term where there is a dielectric of value K, that is epsilon R is nothing but K only. So value of epsilon R is greater than 1. Hence, the capacitance of a capacitor increases when you introduce a dielectric, not even full, but up to some distance also, or up to some thickness also. Now we are going to do is, what will happen? Instead of dielectric, if I introduce a conductor of thickness T, when there is a gap of D. See, this is a parallel plate capacitor and the separation between them is D. E naught is the electric field which is inside it. Now we have introduced a conductor. Remember, it's a conductor now. We are finding the capacitance of a parallel plate capacitor with a conducting slab. This was insulator. First we did was insulator. Now we are doing it with conductor. Now you know it, any conductor inside electric field is 0. This is our basic definition, that V naught is equal to epsilon naught. V naught is equal to E naught into D. Now V is equal to E naught D minus T, because in this region there is the electric field, that is E naught, and in this region inside this the electric field is 0, his thickness is T. Outside in this region, which is not shaded, there the electric field is E naught, and that thickness is D minus T. So E naught into D minus T plus E into T, but E is 0. So this term will not be there. So V is equal to E naught into D minus T. Let us take the ratio C by C naught. C is the capacitance with conductor, C naught is the capacitance without conductor, means there is nothing, there is a air between there, that is C naught. C is when conductor is introduced. So C is upon C naught is equal to V naught upon V. This already I have told you. Now substitute the value of V naught, that is E naught D, and substitute the value of V, that is E naught D minus T. E naught will get cancelled. So it is D upon D minus T. So C is equal to C naught D upon D minus T. Substitute the value of C naught, that is parallel plate capacitor without any conductor. Epsilon naught A by D. dd will get cancelled. Epsilon naught A upon D minus T. Again you can see that C is greater than C naught. Means presence of conductor also between the plates will increase the capacitor. But if the dielectric is there, it will increase the capacitor more. Imagine it now. If I put this conductor completely, not up to T thickness but up to D thickness. So in that case T will be replaced by D. This term will become 0, means the capacitance will become infinite if it is completely filled with conductor. Again I repeat, instead of T thickness, if the conductor is throughout this gap, matlab ki D thickness, then T will be equal to D. The capacitance will become infinite. So when you introduce the conductor completely between the gap of a capacitor, the capacitance becomes the infinite. If you introduce up to some thickness, then capacitance will increase. In case of insulator or dielectric, if you introduce a dielectric of thickness T, then the capacitance C is equal to epsilon naught A upon D minus T plus T by K या epsilon R. And if you introduce it completely, then C is equal to K times C naught. Means capacitance will increase by dielectric times. Say the capacitance of a water is 80. So between two plates, instead of air, if there is a water is dielectric and its value is 80. So capacitance, if you are completely filling them with water, then the capacitance will increase by 80 times. So in general, these are the formula, and these are very important for solving the numericals. These derivations are not there in the textbook, but for numericals it come. So I hope I am clear with it. Further we'll discuss this in the class. Thank you.